All right, hello, welcome back. In the previous video, we saw the concept of inertia extended into 3D rotation. And the last thing that remains is to define equation of motion for 3D objects. So let's do that. So just to, what's happening? I have my frame. Why is it so close? Dissatisfied with my frame. This is my inertia frame. As always, I have my blob of rigid body. And this body is subject to a bunch of forces and maybe moments. This one, that one. And one particular point in the body that we are very much interested in is C. C is the center of mass. So let me write it down. C, center of mass. So, translational equations of motion. Our good old friend Newton told us that for any system of particles, and a rigid body is a system of particles, sum of all external forces acting on the system equals m RC double dot, where RC is the location of the center of mass measured from some inertia frame. So nothing has changed since day one of introductory dynamics in maybe even physics, maybe high school. This equation hasn't changed. F equals ma. Translation is nobody can touch it. Not even going to 3D, 4D, NED. This stays the same. The rotational, the rotational dynamics, we have also seen it before, that for any system of particles, we can write it in two or more forms, that h dot about a fixed point O equals, let me write it as sum of moments to be, no, let me write it to be more analogous to the top one, sum of moments about some point O is fixed, equals rate of change of angular momentum, h dot about O, or we can write the same equation about center of mass, m dot c equals h dot c. And this exact form of equation only works if reference, what did I write? No, that's not reference. Reference point is fixed or is center of mass. Center of mass. If it's any other arbitrary points that may have accelerations, we saw in the past that the equations take another term. Essentially, you have to consider the acceleration of that point too. So those equations, those rotational equations, work for a group of particles, or when all the particles are coagulated and fixed relative to each other in a rigid body. So this equation is it is the equation of motion for rotation of a rigid body too. But that's a little hard. Well, everything is hard to work with in 3D rotation, but that's not informative and useful enough. So let's extend that. So from now on until the end of video, I'm always talking about the equation of rotational motion, either about fixed point or center of mass. And only these two. So I'm going to drop the subscript. I'm going to write h dot equals m, and I'm dropping the summation to this. M is the total moment, external moment acting on the system. So in previous video, we saw H was, let me write it in matrix form. H was I times omega. Now, if I take derivative, H dot equals I dot omega plus I omega dot. And again, to reinforce the notation, whenever I use these curly bracket things, I want to just emphasize that it is a vector, sorry, a matrix version of a vector. So for instance, oops, this omega is a matrix formed by omega x, omega y, omega z. Just to reiterate the notation. And again, I have to say, the textbook uses tensor notation instead of a matrix notation, which looks slightly different, but for the most part, they are very similar. It must be fairly easy to go back and forth between notations. All right, so what does this mean? We have h dot, it has two terms. This one is easy to interpret. So you have some kind of inertia and you are relating the change of angular momentum. The other term is a little harder to wrap your head around. It is a term, it's not zero, and we will see soon another form of it and better equation for it. It is related to how the shape of these inertia matrix is changing with time. As the body rotates, the representation of these inertia values, those in the matrix, also change. So that one is a little, at least to me, harder to wrap your head around what is going on. So let me do one other thing, one other approach. Again, inertia frame. Let me switch now to vector notation. I have H, it's a vector, so this is my vector H. And when I do H dot, what I'm trying to find is the rate of change of this vector as viewed from an inertia observer. So the full time derivative. And it's a vector that is changing with time. What I can do is the same trick that we have been using many times before when we had a vector. I can consider an intermediate frame that is rotating with some rate omega. And first find the derivative of h with respect to this moving frame, and then add the effect of the rotation of the frame itself. And coincidentally, let's assume this frame, the red one, is fixed to the body. So actually omega is the rotation angular velocity of the body. So let me write it down here. XYZ frame fixed to body. So it's a body fixed frame, and omega is angular velocity of the body. So the frame and the body move with the same angular velocity. So I have a frame, a vector that is moving around, a frame that is rotating. The time derivative of my vector h is h dot relative to that frame plus the effect of the rotation of the frame itself. And now this one is easy to interpret. H dot, when you are sitting on the frame and you're rotating with it. So in your view, the only thing that changes in this angular momentum is how fast you are changing your speed, essentially. So it's h dot, so it's not how fast you're moving, how fast you're changing your speed. So this one is I, and now I'm going to switch back to matrix notation. I omega. And the next one, omega cross h. What I can do to write it in matrix notation, I can do omega tilde times my h vector written in matrix form. And remember what this omega tilde was. Let me add a note. Whenever you have omega cross a vector times a, what you can do is to convert it in matrix form. Matrix form. You can do omega tilde times this a, where omega tilde is what we had before. It's 0 minus omega z, omega y, minus omega x, 0, omega z, minus omega y, omega x, 0. So it's the same equivalent of cross product, but written in a matrix notation. I wanted to add something else. Did I want to add something else? No, that is all I wanted to say. So in this matrix form, now let's do this. H dot equals I times omega plus omega tilde times h, where h itself, this one, is I omega. So omega I omega. And this is the matrix form of what we call Euler equations. And if you take it next to this one, which is a Newton equation, what you end up with is something called Newton-Euler set of equations that describes both rotation and translation of a rigid body in a space. I don't know the historical facts, but I don't think Euler actually worked with, maybe he did, I don't know, work with matrix form. You can expand this equation into essentially write down the 3 lines of that equation. What you end up with, spoiler alert, going to be very long, so feel free to speed up the video or skip a few minutes until I write this and I come back. So it's going to be ixx omega dot x plus ixy omega dot y minus omega z omega x plus I xz omega dot z minus omega x omega y plus izz minus iyy omega y omega z plus iyz omega squared y minus omega squared z. No way. Why did I miss this? Equals m. Equals mx y xy omega dot x plus omega y omega z plus iyy. Yep, I don't need that. Omega dot y plus iyz omega dot z minus omega x omega y plus ixx minus izz omega z omega x plus ixz omega z squared minus omega y x omega x squared equals my x z omega dot x minus z plus iyz omega dot y plus omega z omega x plus izz omega z plus iyy minus ixx omega x omega y. Wait a second. Let's see. X. Okay. So these are the equations. These are also called Euler equations. One thing I before I forgot to include this m here. So if you had skipped the video, just note that I forgot to write the total moments there. And yeah, these are the equations of rotation. So you can do quite a lot of things with this. So one thing is, for instance, if you have, what's happening? If you know what your moments are on a body, you can use it starting from some initial condition and solve these three differential equations in terms of omega x, omega y, and omega z. And solve for those, find omegas, and possibly use the equations that we had before, use omegas to solve another set of ordinary differential equations to find orientations. So you can go from moments to accelerations to velocities to orientation in 3D. You can go calculate omegas, take integral or use this OTE, get omega, and from there get orientation. So you can see how your body will rotate in space. So as you can see, these equations are significantly more complex than Newton's equation, which was m x double dot equals f, or my double dot equals fy. And one thing very interesting about 3D rotation is the existence of a lot of these coupling terms. So it is, as we'll see in the next video, it is possible to have no acceleration, no omega dots, with still having some moments. That is because of these couplings that exist between different axes of angular velocity. And I want to again emphasize, going back up here, that these equations are valid if your reference point is either fixed or the center of mass. And this is something I wanted to mention and I forgot. So let me go. Okay, zoom a little. This is my original size. So compare this equation and that equation. So on one hand, I have h dot is I dot times omega plus I times omega dot. And then the other equation I have, let's call it plus, this is I omega dot. I omega dot plus omega tilde times h. So comparing these two, actually you can see, well, don't compare that one with this, compare it with this one. That now my I dot times omega has become omega tilde times I times omega. So in other words, note I dot is in matrix form, omega tilde times what? Times I. Essentially some kind of cross producing omega with the tensor of inertia. So something to remember. All right, so that is all I have for this video. These equations are gigantic. I still don't have any intuition. I see the math and I know it works, but I don't have much intuition. In the next video, let's look at one very simple example, hopefully to make this a bit more concrete, give you a little more information how we can use it. All right, see you then.